So we're going to go ahead and talk about work, but with angles. And these tend to be one problem per test. So you're going to guarantee have one of these questions on the test. So let's look at our first scenario where we have a wagon that's being moved horizontally. It's traveling with a speed of 5 meters per second. That's going to remain that way. It's receiving a 30 Newton force as pulling it. So this is the 30 Newton force at an angle of 60 degrees above the horizontal. It ends up displacing 20 meters. So if this problem wasn't completely greatly stated, but we're going to go ahead and assume that there was no change in the motion because it wasn't said as such. So for our practical purposes, we're going to assume this remains constant. And if it remains constant, there's no change in kinetic energy. And if there's no change in kinetic energy, then no work was really done by this velocity here. Okay, the work is actually being done by this force that's being applied to the wagon. However, it's not being applied completely parallel to the direction of the wagon. So we're going to go ahead and formally state, we know in the past we said that work was equal to force times displacement, and that it was going to be parallel displacement. Well, that's very much true. But what happens if the force is not being applied parallel to that displacement? Well, we have the horizontal component of that force that's being applied. So in this case, we would say that the work being done on the cart is going to be the 30 newtons times cosine of 60, right? That's because if we were to go ahead and draw our triangles, this is fx, this is fy, and fx is going to be f times cosine theta, fy is f times sine theta, and we want that parallel horizontal component. So many times the work formula is actually written as such, fx times delta x, fx being understood to be the cosine. So if we go ahead and type this in a calculator, we're going to get 300 newtons. Make sure you're using degree mode. Here's another problem, but this time the object is being pushed at. So instead of being pulled, it's being pushed. We do know that the mass of this is 2.5 kilograms, which if we need to convert it into a weight, we can if we need that force in the future. But it displaces a total of 2.20 meters. This applied force is 60 newtons, and this theta is 25 degrees. Determine the work done by the applied force. So this is work is fx delta x. Now this is the work applied by the force. So this is the force of 60 newtons. But it's at an angle, so I need to do the cosine. And then this displacement of 2.20 meters. That ends up being 31.9 joules for part A. Part B, the work done by the normal force. So the normal force is going upwards like this. It forms a 90-degree angle with the horizontal. So if we want to be technical about this, this is applied force. We'll do WA for applied force. This will be WN for the normal force. This is going to be the mass, which is 2.5 times 9.8 times cosine of 90 times 2.2. But folks, what is cosine of 90? That's 0. And I'm sorry, I'm actually doing part C instead of part B. My bad. So let's switch this up a little bit. This is part C, gravity, my bad. Because the normal force is not the weight. The normal force is actually different in this case. But regardless, here's part C, so make sure you make that correction. This is the weight of the object. This is cosine of 90, because, and I'm sorry, I'm tripping. That's not even cosine of 90, that's cosine of 0. It's going down this way. Or I guess it could be 90, depending on how you're looking at it. Yes, it's 90. My bad. 90. 90, 90, 90. Wake up over. Okay. Just going downward. We have cosine of 90. That's 0. So the work done by the force of gravity, aka the weight, is going to be 0. Now part B is also 90 degrees. That's going to be the work due to the normal, which we could set up Newton's laws for that, right? We have a force going down, and this is going down, so the normal force is actually going to be equal to the weight plus the sine component of the applied force. Don't even worry about that. You don't even need that because, again, it's cosine of 90 degrees. And cosine of 90 is 0. So what we're showing you here is that there are multiple forces acting on an object, but if they're perpendicular, they have no bearing on the work being done because cosine of 90 is 0. Anything outside of that will go ahead and actually contribute to the work being done. Now, as far as the net force on the block is concerned, you would add up all three of these answers. So part D, the work done by the net force is going to be, add all three of those up, 31.9 joules. Here's a conceptual problem that tends to be a favorite among AP tests. And we have here 4 scenarios. We have the direction of the displacement going in a positive x direction, and then we have this applied force. The question being to order these in the correct order from the amount of work done from the most positive to the most negative. Now, the most positive is going to be, of course, or the stronger, or the greater the magnitude of the work is going to be with anything that's parallel to the direction. And in particular, if that angle appears to be 0 degrees, right? That's what we did last time with the last videos. So, looking at these options, this is going to be the most work. And on top of that, the positive work. The most positive work. Because the force is being applied, it looks like it's parallel. The other one is parallel is B, but it's going in the opposite direction. So we could almost instantly say, well, okay, this will be the most negative work that's being applied. Now, if we want to consign ourselves to the options, right, that means we're going to start with C, we're going to end with B, so the answer is this one right here. This is the right order. But let's go ahead and go through each scenario one by one. So we're saying this is the most positive work done because both are going in the same direction and it's parallel. Next is going to be A. Well, we already noticed that if it's perpendicular, then the work is 0. But 0 on the number line is further to the right than negative numbers. Okay? Because with D, we actually have negative work that's being done. And it's not even the most efficient work being done because it's at an angle, right? It's not quite parallel. So we end up only using the horizontal component of this work, not the full value or magnitude of the force that's being applied. And then that leaves us this last one here with it having the most negative work. The magnitude is the same as C, but the sign is different.